Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're beginning our investigation of amines and are going to look at the preparation of amines. Now, one of the most obvious preparations of amines is the nucleophilic substitution reaction, or the SN2. This reaction involves the reaction of ammonia, which is a powerful nucleophile, with methyl iodide. The reaction goes SN2, and because ammonia is a powerful nucleophile, it does backside attack, and we kick out the iodine, and that will produce the protonated version of the amine. And we'll lose I minus, and we get a methyl aminium cation. Now, another amine can come in and grab the proton. If there's excess ammonia around, that certainly can happen, and you'll get ammonium cation, and you'll produce H2NCH3, methylamine. Now, one of the problems with this reaction, or this type of reaction with alkyl halides, is the fact that amine is also a powerful base. If we go beyond methyl iodide, because amine is a powerful base, you can get competing reactions, significant competition with the formation of alkene, elimination reactions. Now, this can't happen with methyl halide, and certainly is not a problem in this case. But as we progress from primary to secondary alkyl halides, more substituted bonds are more stable, and with a powerful base, you get more and more likelihood of forming alkene. And so one might say, well, could this go SN1 with a tertiary? By the time you get up to tertiary alkyl halides going SN1, you would get appreciable amounts of alkene formation. But there is another problem that occurs with this reaction, and that is that the product is a powerful nucleophile. It is a powerful nucleophile. Now, the net consequence of having such a powerful nucleophile forming is that as it builds up in concentration, it can begin to compete in the reaction with the methyl iodide. And if it does, we go SN2, backside attack, minus I minus, you can form, right, H2N bracket CH3 twice positive. And if the same thing happens as before, ammonia can come in, go off as NH4 plus, and you will get HNCH3 twice, dimethylamine. Well, likewise, this process can continue. You can get dimethylamine, CH3, twice, and H, competing. I'm not going to draw out the whole mechanism again. So methyl iodide, it reacts with methyl iodide, it goes SN2. It'll go through all the steps and end up producing trimethylamine. And then finally, of course, trimethylamine can undergo the same steps. But because there's no proton to pull off this time, we put a fourth methyl on, we'll be stuck at the tetramethylammonium cation. So this last step here won't happen for the trimethylamine after it attacks methyl iodide, because it will end up producing 4 methyls around the nitrogen. There's no hydrogen to deprotonate. And you actually form tetramethylammonium cation. Well, it would have iodide as its counterion. So there is a series of competing side reactions. Now, we've run into this problem before in free radical monohalogenation reactions, where competing side reactions can eventually take you from chlorine reacting with methane to make methyl chloride. Methyl chloride reacts with chlorine to make methylene chloride or dichloromethane. Dichloromethane reacts with chlorine to make chloroform, and chloroform reacts with chlorine to make carbon tetrachloride, and you end up substituting a carbon with 4 chlorines. This is much the similar thing that we saw in free radical monohalogenation. And although we have all these factors combining to make this reaction not very synthetically useful, we have the fact that it's a powerful base and can get alkene formation, you have these side reactions. You can do a few things in the methyl halide case to favor product outcome. For example, if I want to produce methylamine as my major product, all I have to do is use a vast excess of ammonia. Okay? If I use a vast excess of ammonia, when we produce a product, there's very little methyl iodide around. Methyl iodide's dilute. And so the methylamine that forms is also hugely outnumbered by the ammonia. Based on this, the probability of molecular collision between methyl iodide and ammonia is much greater than the small amount of methylamine produced, because there's a huge excess of ammonia. And of course, to react, you must get molecular collision. So by using an excess of ammonia, what will happen is when we consume all the methyl iodide, we will have a tiny amount of methylamine and a huge amount of ammonia. You then can separate the ammonia from the methylamine based on boiling point. Collect off your product, cycle the ammonia back, expose it to more methyl iodide, and continue the reaction. However, if you prefer and would rather make the tetramethylammonium iodide salt, okay, well then all you have to do is use excess methyl iodide. Once all the ammonia reacts, the methylamine begins to react. There's lots of methyl iodide around. Once all the methylamine is consumed, the dimethylamine reacts. And finally, the trimethylamine reacts. And you end up doing this. So, yeah, this can be formed with excess methyl iodide. However, this guy can be formed with excess ammonia. All right. So Very important to take note of that. Now this reaction is controlled in terms of rate by steric hindrance. It's your standard SN2. All right. So another thing to note is as we go from methyl to primary to secondary, not only do we get production of more and more alkene as a side product, but the reaction does slow down in relative rate. Okay. Well, there is a nicer way of making primary amines, which goes back to some chemistry that we covered in the carboxylic acid section of the course. And that is the Gabriel Phthalimide Synthesis. Okay. Now the Gabriel Phthalimide synthesis is a synthesis of a primary amine. Okay? A primary amine. And it really functions on the basis of the increased acidity of alpha hydrogens. A hydrogens next door to off of carbons or other atoms next door to hydrogen, next door to carbonyl. Now, we learned, and I'm not going to look at the mechanisms. These mechanisms are covered in your notes. And we've also looked at them. If you wish to see them, you can go back and examine the podcast on dicarboxylic acids. And on anhydrides. Here's a dicarboxylic acid called phthalic acid. And we learned in the previous Scribblecast lectures that if you apply heat to phthalic acid, it will close, eliminating water, and form an anhydride. And you will form a molecule called phthalic anhydride. Phthalic anhydride can be reacted with ammonia. And in the anhydride or amide section, can't remember which, but one of the carboxylic acid derivative sections, we looked at the mechanism for this. And if we hit it with ammonia, we can produce phthalimide. In fact, formation of phthalimide is so important to this reaction that, well, since we looked at it in the case of succinimide, we might as well look at the mechanism for this step. All right? And so this molecule is referred to as phthalimide. How do we convert phthalic anhydride into phthalimide? Well, let's take a look. I'll start with phthalic anhydride. Anhydrides are carboxylic acid derivatives, and as we've already established, when exposed to powerful nucleophiles, can undergo nucleophilic acyl substitution. And if I do this, so we now have an O minus here, and we have an NH3 positive that has added. All right. Now we can dump in a lone pair, reform our pi bond. This bond will break, and when it does, giving me an O minus here. Double bond O has reformed, and here we have our NH3 positive. Well, one thing we learned when we looked at carboxylic acid derivatives is that amides are not basic. A protonated amide like this, therefore, is very acidic, would want to lose its proton very quickly. And plus the fact that you're in the presence of amine. Ammonia can come in, grab a proton. So, if you like, NH3 comes in, goes off as NH4 plus. And you are finished. You have a double bond O minus. So here's where the NH4 plus associates with carboxylic, the deprotonated carboxylic acid, the carboxylate anion, and we have a nice amide here. Now, this guy certainly would be in equilibrium. And if you added H plus to the ammonium salt, you could get carboxylic acid here with the NH2. Now, in the presence of excess amine, there's less water around to drive the nucleophilic reaction backwards. And as a result, this amide has a lone pair here. And that lone pair, although it's not hugely basic, hugely nucleophilic, because it's an intramolecular reaction, molecular collision can occur with the carbonyl. And in the presence of heat, this certainly does happen. And if it does, you will form heat. You'll get an O minus and OH is here. Still have the double bond O here. And now you will have an N with two H's off of it linked up. and of course it will be positive. Now, a series of reactions can take place. Electron movement. 2 electrons from a lone pair can reform the C double bond O. The hydroxide can leave. And this may or may not grab the proton. I think in the example in the notes it actually grabs the proton. And we go directly to the end. But if it didn't, you'd have a very short-lived intermediate. And what's going to happen to this nitrogen in the middle very quickly is either ammonia would come in and grab the proton, or the OH minus you kicked out grabs the proton on the way out. But very quickly, a proton is lost. And that proton could be lost even before you reform the carbonyl. And you form your phthalimide. Okay? So it's possible to go right through to the phthalimide. Of course, phthalimide, being an amide, is not the molecule we're really after. What we're really after is how it can be used to make unsubstituted primary amines. And I want to leave this mechanism up if I can, so we're going to work in this small open area underneath, and I'll show you why I want to leave this mechanism up. Well, the first thing to note is that amides are not very basic, and even though there's a lone pair, they are not very basic because that lone pair is resonance stabilized into the carbonyl. And when you have 2 carbonyls, that lone pair is even more delocalized and even less basic. Now, because it's not very basic, what's interesting is just like alpha hydrogens off of carbon, this alpha hydrogen off of nitrogen becomes more acidic. And it's due to resonance. That is, if I deprotonate the phthalimide to make the deprotonated phthalimide anion, now I have 2 lone pairs, and it's negatively charged. Well, I can draw resonance contributors for that negative charge, being delocalized over both oxygens of the carbonyl. So there you have that, where I dumped in the lone pair this way and moved the pi electrons out onto the oxygen, putting negative charge on oxygen. And certainly I could do the same thing to the other oxygen. There's one lone pair here. So the net result of this is this, what I can deprotonate this guy in base very readily. So in base, a deprotonated phthalimide anion forms. All right. Well, the phthalimide anion turns out to be a fairly powerful nucleophile. It can be reacted with methyl primary or secondary alkyl halides and produce used to produce primary amines. The attack, of course, is SN2. So let's just remove our resonance stabilization that we know is there. Look at the anion and react it with methyl iodide. And what happens? We react it with methyl iodide. We get an SN2. The nucleophile does backside attack on the iodine, backside attack on the carbon, kicking out iodine. And once that happens, you produce N-methyl phthalimide. Well, certainly N-methyl phthalimide. N-methyl phthalimide is not a primary amine. It's an imide. But backside attack can yield this. What's really nice is, and the reason I kept this mechanism up, is we can alter this mechanism slightly and show you how you yield the primary amine from N-methyl phthalimide. So one of the changes I have to make this to this mechanism is we're going to run it backwards. And I'm going to, in black, show all of the changes. So instead of the H here, I have this methyl. And we are in base, so we're not going to create a protonated species here. But what's going to happen is we're going to have hydroxide attack, and it's going to add to that carbonyl. And lo and behold, we don't have a positive here. We have our N-methyl. And look, here is a hydroxide. So we get this hydroxide attached, and the electrons can reform the carbonyl, kick out the amine, and if you do that, you will very quickly get this NCH3 with two lone pairs. Right? Get this carboxylic acid with this NCH3, and so there's a minus charge. Now this guy, I could resonance stabilize this negative charge out to the carbonyl, and that is drawn for you in your notes. But what's interesting is very quickly the OH will deprotonate, making the O minus, and you'll get NHCH3. All right. In the next step, some changes take place. So this very quickly goes this way. In the next step, hydroxide attacks again. OH minus attacks again. And it has lone pairs here, and it attacks here. And so what we have here now is our NCHCH3, and we have O minus and OH. So when we reform the carbonyl and we kick out NHCH3, we now form double bond O, O minus. Well, actually, that's an OH, right? And we have the O minus up here. And what do we kick out with it? Well, we kick out NHCH3. Okay. 2 lone pairs, and it's negatively charged. So this is a methylamide that's very, very basic. So that when we're done, well, you get an O and an O minus. And of course you have NH2CH3, grab the proton. So there's some changes that take place in the mechanism because we're in base and we're going backwards to a different product than we started for, but there's a great similarity between the formation of the phthalimide from the anhydride and then the conversion of the methyl phthalimide back to dicarboxylate. Much of the reaction mechanism is similar. All right. Okay. So, let's look at what happens one more time. We can put the plus NH2 down here, make it a little larger. We start out with this N-methyl phthalimide. The base does an attack on a carbonyl, making this alkoxide. Okay, this alkoxide O minus. And when it reforms the carbonyl, you break the N bond, you're producing your carboxylic acid, and this resonance stabilized negative charge on the amide. Now, it's sufficiently basic and this is sufficiently acidic that the proton can transfer. Okay, it abstracts a proton, you get the carboxylate CO minus, and you have this amide. Hydroxide attacks again, giving you this O minus OH. The minus reforms, kicking out NHCH3 as the amide, a negative charge on nitrogen. The carbonyl reforms, you have an acid here. And this amide's very, very basic, very basic. It'll grab a proton from solvent, whatever around, and the acidic, the carboxylic acid, you're in base, will deprotonate, and you get dicarboxylate. So you end up with forming or kicking out a primary amine, okay? Note it is primary, a primary amine, and the dicarboxylate. Now this reaction mechanism can be extended to form another group rather than just simple primary amine. If this methyl right here off of the nitrogen was more complicated, then the methyl in the product would be more complicated. And if we put a very large group, okay, here, say something that looks like, oh, I don't know, how about this? Let's use black. Instead of CH3, what if I had a C attached to nitrogen? A CH3. And 2 C double bond O's. And an O, CH2, CH3. So an O, CH2, CH3. And that was attached to my nitrogen. So I had this. Well, you can see this would not have changed this mechanism. What we'd have off of here is, in our product NH2 that got kicked out, we'd have this big side chain off of this carbon. We'd have this C double bond O. What's interesting about this is once you get this, I'm going to just put R3 here to indicate this big group, is that CR3 could very quickly, in acid and heat and H3O+, be converted to NH3+. You'd have the C. That C would have a methyl off of it. And you'd retain one of the C double bond O's, which would become a carboxylic acid. You could very quickly form a molecule that looks like this. And we've seen this type of molecule before. What is it called? It's called an amino acid. So this Gabriel Phthalimide synthesis not only can create primary amines, but it can have the primary amines attached to a group that will yield a carboxylic acid functional group attached to it, and you produce an amino acid, an alpha-amino acid. Well, obviously we want to look at a couple things here. One, how do I produce this group attached to the N? And two, once I kick it out, how does acid and heat produce the amino acid? Well, let's answer the first question. Remember, the mechanism is exactly the same. This CH3, whatever this CH3 is, it doesn't get affected. I mean, it could be this CR3, this big bulky group. And when it finally gets kicked out, you have an NH2 attached here. Okay, so let's take a look at how we could make this big group attached to the phthalimide. Now, one of the things that stands out is clearly I can begin by making or get close to this type of group from this molecule, a dicarboxylic acid, a fairly common dicarboxylic acid. This molecule is just malonic acid, and so let's take a look at that molecule again and use it as a starting point. Now, if I hit malonic acid with base, I'm not going to get anywhere. If I hit malonic acid with base, I'm going to just deprotonate the carboxylic acid groups, and we don't want to do that. So what I'm going to do is I'm going to hit malonic acid with SOCl2 and make the acid chloride, the diacid chloride, if you like. Mononyl dichloride, I guess I would call this. And then I can hit that with base, such as ethoxide, OCH2, CH3 minus. And if you're going to use ethoxide as your base, always use the conjugate acid as a solvent. So here's my ethanol. There we go. And I'm going to produce now the diester, diethyl malonate. So here we go. Here's the diethyl malonate. I take diethyl malonate now, and I can hit it with base. I can use the same base again, if I wish. In fact, I prefer that because I want to prevent transesterification. I want to keep the ethyl ester. And to prevent transesterification, use the same base as the ester group. We have an ethyl ester, well, let's use ethoxide. And again, that is in ethanol. I take the malonate, that will deprotonate it, and I will produce a resonance stabilized carbanion. We've seen this in the enolate carbanion section a few lectures ago. And I can draw a resonance contributor where I dump this lone pair out towards the oxygens. I can dump it to the left. Oops, I forgot an oxygen here. Sorry about that. Should be an O, CH2, CH3. So if I do that, I get CH3, CH2O, CO minus, double bond CH, C double bond O, O, CH2, CH3, so resonance stabilized with the enolate. Likewise, I could have dumped the electrons towards the other carbonyl. If I do that, I get CH3, CH2, O, CO minus. The enolate on the other side, which leaves the C double bond O intact on the left, and my OC. CH2, CH3. Okay. So this whole species is a resonance stabilized carbanion. Now this resonance stabilized carbanion can be used and can be alpha-bromonated by reaction with Br2. If I react it with Br2, the minus goes for one of the bromines, you kick out bromine minus, and you can make a secondary alkyl halide. which has all these extra functional groups on it. So you have a CHBr. Now think back to the phthalimide anion. The phthalimide anion attacked alkyl halides because it was a reasonable nucleophile. Well, we have an alkyl halide, just like methyl bromide, except in this case it's secondary, so it's going to react a little slower. But the phthalimide could do backside attack on this molecule. Okay. So you get Br minus. So this is how we make that big unit I showed you. Well, what happens next? Well, we take that big unit with the phthalimide anion, okay, and we have N minus here, and we now have the CHBr with the C double bond O. Actually, let's put the Br right here, the H over here. We have a C double bond O. And then we have this O, CH2, CH3. O. And the minus can do backside attack, and you'll kick up Br, and you'll do this SN2, because SN2 will work with secondaries. So that when you're done, instead of having N-methyl phthalimide, you have a substituted phthalimide with this humongous organic diester off of it. You have a C and H, a C double bond O, O, CH2, CH3, and a C double bond O. Now, I showed you the mechanism already for the breakdown of this in base. Hydrolyze this in base, right? And you can kick it out if you wanted to make glycine. But what's interesting is this group is acidic. Let's just mark that. This is an acidic proton. I certainly can deprotonate that if I hit it with CH3. Because one of the things we had was we had a methyl here to make our amino acid. How did we get the methyl in this position? If we hit this with CH3, CH2O minus to prevent transesterification, and we do that in ethanol, we certainly can deprotonate that proton. If we do that and deprotonate it, we'll get this. So we'll get C, C double bond O, O CH2, CH3, C double bond O, O CH2, CH3. And just as usual, our carbanion is resonance stabilized out with the enolates. I could draw 3 resonance structures with this. But I can hit this guy now with methyl iodide, and it will do an SN2 attack on the methyl iodide. If it does that, I get backside attack, I will get the substituted phthalimide we had in the previous mechanism. And it will have a methyl here. This is the exact fragment we had. And this fragment very readily kicked out amine, so that I could draw CH3, CH2, O, C double bond O, C, that has a methyl, and it has an amine. So I very quickly would spit out a primary amine from the hydrolysis in base, if you like, and we could use hydroxide, and we'll talk about the consequences of using hydroxide. Certainly, at this stage, we would probably do it in acid, so we could hydrolyze an acid that may protonate the amine. Right? So if you did a hydrolysis in acid, several things would happen. And let's talk about, well, the phthalimide gets hydrolyzed, and because you're an acid, you would produce the protonated salt. But acid would also hydrolyze something else. Do you recall your carboxylic acid derivative chemistry? Hydrolysis of esters would occur. And what do esters hydrolyze to? Well, they hydrolyze to dicarboxylic acid. So we could hydrolyze right through the dicarboxylic acid. And the mechanism for that is given in your notes, both in the carboxylic acid section and in this section of the amines. Okay, while we hydrolyze the dicarboxylic acid, now if we throw in heat, we can do something called beta decarboxylation. If we did acid with heat, we could kick out a CO2, and the mechanism for beta decarboxylation, of course, has been covered in your previous scribble casts on dicarboxylic acids, and it was given in your notes as well. But you essentially kick out a CO2. And the mechanism is given for that, and if CO2 gets kicked out, well, you're left with an H attached to the carbon. And lo and behold, here's your amino acid, right? Amino acid, alpha-amino acid with CH3, that's alanine. Now, what if we left this acidic proton intact? What if we didn't put the methyl on? Well, we would have had an H here, and that would have been the amino acid glycine. So this Gabriel Phthalimide synthesis, in conjunction with malonic acid derivatives, malonate esters, can be used to make alpha-amino acids. This is a very, very powerful synthesis. Okay. Well, we've covered a lot in the preparation of amines, and there's some more preparations we need to look at, but I think this is enough for this Scribblecast lecture. We'll pick up with the preparation of amines and then begin looking at some of the reactivity of amines in the next Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.